Welcome to Day 2 of Lesson 7.6 when we're solving equations involving logarithms. First main concept of the day basically is telling if you have two logs that are equal to each other and they both have the same base, then what you're taking the log of also has to be equal to each other. So this statement reads, if b, x, and y are positive numbers, and as long as b does not equal 0, I see a typo there, does not equal 0, then log base b of x is, when log base b of x is equal to log base b of y, x and y must be equal to each other. Now this statement is written with that abbreviation IFF, meaning if and only if. So this statement is true whether you read it forwards, left to right, or from right to left. So it also would be true if I have x equal to y, then log base b of x is equal to log base b of y. Let's see how we're going to use this. Here is a log equation that we're trying to solve. Log base 5 of 4x minus 7 is equal to log base 5 of x plus 5. Because both sides of the equation are log base 5, I can then say that 4x minus 7 is equal to x plus 5. In one simple step, this log equation, typical algebra 2 problem, becomes an algebra 1 problem where you're just simply solving for x. I'm going to subtract x from both sides, add 7 to both sides, and then divide by 3. So x is 4. You should always do a quick spot check, taking a look at x, and when you put x in place of x in the original equation, don't worry about what the log base 5 is of it. Check to see the calculation 4x minus 7. Will that still give you a positive number? Check putting 4 in this statement. Will that still give you a positive number? Because remember, in the original statement, b, x, and y all have to be positive numbers, again, and b is not allowed to be equal to 0. Let's take a look at a new kind of equation. With each of these equations in Lesson 7.6, oftentimes the instructions at the beginning of each section of problems will give you a hint as to how to solve. And this says solve by exponentiating each side. What that means is the given equation, you are going to make the exponent of the new equation you are going to create. So this statement on the left side, log base 4 of 5x minus 1, is going to become the exponent. You just have to pick the base that this statement will become the exponent of. Now, if you make this an exponent, you also are making the 3 an exponent. What base should you be picking? Well, again, when you read what this statement is saying to you, this is log base 4. There you go. You are going to create a new equation with base 4 where this left side becomes the exponent of base 4 and 3 becomes the exponent of base 4, looking like this. Then recalling from a previous section, whenever you have a base and the exponent is log of the same base, in essence, you can think that this 4 and the log base 4 basically cancel out. And so the left side of my equation simplifies to 5x minus 1. The right side will simplify to what 4 to the third is, which is 64. And once again, in one simple step, you've changed this problem from an Algebra 2 problem to one you know how to do easily that you learned in your Algebra 1 course. We're going to add 1 to both sides and then divide by 5. Quick double check, 5 times 13 minus 1, yes, that will still be a positive number, so 13 is a good solution. Let's look at one last example. Once again, we're going to solve by exponentiating each side. But this problem is a little bit different from the previous one because it is indicating that we are taking a sum of two logs. You also might notice that we don't have a base written in. Does that mean there isn't a base? No. When you just see log and no base written, that is the common log. We do not take the time to write base 10 because it happens so frequently, or in other words, it happens so commonly. We just know that it's a base 10. To make this problem look similar to the previous one, I'm going to have to remember how to condense logs. And recalling that addition of two logs of the same base allows me to merge them into one log statement when I'm multiplying. So don't forget that addition becomes multiplication when you are condensing logs. My next step, I'm simply going to simplify what I'm taking the log of. I'm going to distribute my 5x to the x and to the negative 1. So now my statement looks like common log of 5x squared minus 5x is equal to 2. Now it looks like the problem we had on the previous page. I'm going to exponentiate both sides, meaning I'm going to make the left side an exponent and the right side an exponent. What should be my base? Well, what am I taking the log? What is my log's base? It's that invisible 10. So I'm going to exponentiate both sides, where the left side becomes 10 to the exponent log base 10 of 5x squared minus 5 is equal to 10 squared. Once again, that 10 and that common log will cancel. My left side simplifies to 5x squared minus 5, and the right side becomes 100. Now what we have is a quadratic equation. And we need to remember that when you solve a quadratic equation, it must be equal to 0. So I'm going to subtract 100 from both sides. Then I notice that each of these coefficients in this constant term all have a common multiple of 5. So I'm going to divide every single term of this equation by 5. Now that looks a lot easier to solve. Solving a quadratic is something you learned how to do in your Algebra 1 course, and we've reviewed it again in Algebra 2. You have many ways to solve. What will work 100% of the time is the quadratic formula. But we all know that using x equals opposite of b plus or minus the square root of b squared minus 4ac, all of that divided by 2 times a, takes some time and a lot of paperwork. So let's look and see if there's another way. Maybe factoring would work. So we're looking at, are there any factors of negative 20 that would sum to negative 1? Let's factor it into 2 binomials, if that is the case. And definitely it does work, because negative 5 times 4 is negative 20, and negative 5 plus 4 is negative 1. We have just factored it. Why did we factor it? Because we now know anytime you have a multiplication where you have a times b and the product is 0, that means either a is equal to 0, that means my entire x minus 5 is 0, or b, in this case x plus 4 is 0. Solve each little mini equation, and it appears that I have 2 answers to this log problem. But don't forget the last step. Double check when you put what you solved for x into the original problem. Are you taking the log of a positive number? When you put 5 in place, definitely you're taking the log of a positive number. But when you put negative 4 in place, 5 times negative 4 is going to be a negative number. Negative 4 minus 1 is going to be a negative number. We have to eliminate x equals negative 4 as a possibility. We did all of our calculations correctly, but we ended up creating what we call an extraneous solution. So you need to eliminate that answer. Once again, that answer is being eliminated not because x is a negative number, but because when you put it back into the statement what you're taking the log of, it's making you take the log of a negative number. Today's assignment is pretty much to finish the rest of the worksheet, 28 through 42.